the value of t must be stored in a latch. Okay. So, I will the changes begin if load is 0, load 0 active, then data will go to t and d out will be generate a latch. Looked at the different ways of assigning some values to variables. One is using the assign statement, another is equal to the equal to statement, another is less than equal to. So, what are the differences between these? Assign you have already seen, but what are the other two? So, we shall be seeing this in our the various features of the language Verilog. So, in this lecture we shall be discussing about the various Verilog operators. Like in any programming language, well, you can take as an analogy C, C++ or Java, there are some operators which are built in the language which can operate on some data items, some numbers, some characters, some values, and they produce some results. So, in the same way in Verilog there are a set of operators, as you shall see, some of them are very similar to the operators which are available in high level languages like C or C++, but there are a few others which are very specific and they have some direct connection with the hardware that Verilog is supposed to model. Okay. So, we start with this lecture on Verilog operators. So, we start with the most basic kind of operators which you see in any language, the operators that allow us to carry out some arithmetic. These are the so called arithmetic operators. Now, broadly speaking, if you just think of the arithmetic operators, so these operators can be broadly classified into either unary or binary. Unary means this kind of operator will be operating on a single operand or data item. Binary means it will be operating on two data items. But some examples of unary are, you are quite familiar with this kind of notation. You can write plus a or you can write minus b. These are something which is quite valid in expression. We can write minus within parenthesis, let us say a plus b. So, these minus and this plus, these are unary operations. They are working on a single data item. So, in the first case this is a, here this is b, and here this is this whole thing. This minus is operating on this whole thing. And operators that are supported are as follows: a multiplied b, and so on. There are several others. Okay. Let us see. So, in Verilog, the operators that are supported are as follows. So, you have two unary operators, one is plus, one is minus, and among the binary operators, some of them I have already mentioned. You have addition, subtraction, multiplication, division, modulus. Modulus means you divide by the second operand and take the remainder, and double star means exponentiation. Some of the examples are shown here. This is an example of a unary operator minus, while this plus is a binary operator. Here minus, star and plus, these are all binary operator. This minus is working on a and b, star is working on c and d, and this plus is working on this first number and the second number. Similarly, this slash mod exponentiation, this means a to the power 3. Okay. These are the so called Verilog operators, and here as you see that the Verilog operators are somewhat very similar to what you see in the other programming languages like C, with the exception of the exponentiation operator. The others are means almost the same as those available in the language C or C++. Okay, fine. So, let us move on. So, we now look at logical operators. Well, when we talk about arithmetic working on C and D, and this plus is working again very similar to the language C or C++, such things are available there also. So, these operators both logical expressions or values true or false, and you are defining the logical AND operation will, if A is true, not. So, the point to note is that, so while you are evaluating such expression, like when I have written done and ACK, the values of these two variables done and ACK, if the value is 0, then it will be treated as false, but any non-zero value will be treated as true. And as I said, the logical operator will return the value again. Fine. Now, let us come to the relational operators. These are again a very relational operation. They operate on numbers. So, Verilog is for and tilde hat is exclusive NOR. So, we have already seen some. Next, there are some bitwise operators. Again, these bitwise operators, not exactly all of them, some of them at least, are available in the language, is supposed to model a hardware, and at the level of hardware we talk about bits, we talk about the logic operations. So, these bitwise operations are very important in Verilog, because at times when we just model some logic expressions at the bit level, we use this kind of bit level operators. Okay. So, the bit ORed with the value of b. Similarly, in the second statement, which is actually similar to the evaluation of the OR plus. Now, what is a reduction operator? Reduction operator is trying to reduce a set of items into a single item. This is from where the name reduction comes. Just operate operator. It converts. This is bitwise OR, tilde AND is NAND, tilde bar is NOR, this is XOR, tilde hat is exclusive NOR. Well, how we just use this kind of reduction operator? It's simple. Suppose I have a variable, a single bit and the output you have used. So my just initial values are A is 111. Next comes the shift and conditional operators. Now the first two kind of shift operators are available in a language like C, which simply specifies right shift or left shift. So here, let's say in the example I've given, we have defined two variables, data and target, a vector of size 16. So if I say data right shift by some register, okay, time shifting shift. So what does arithmetic right shift means? Its basic purpose, you need to understand the 2's complement number system very clearly. So just to refresh your memory, so here we'll indicate the sign. 1 means, so the other bits will be something, let's say 8. Left means multiply by 2. Now for a 2's complement number, if you want to implement shift right, the rule is that if the number is negative for shift right by 1 position, shift right is actually equivalent to division by 2, shift right by 1 position, and shift left means multiply by 2. Now for a 2's complement number, if you want to implement shift right, the rule is that if the number is negative for negative numbers, you shift in 1, and for positive numbers, you shift in 0. So you see, to implement such, this is called arithmetic shift because we are doing some arithmetic operations here. To implement this, what we have said is that you see, for a normal right shift, we said that always 0 will be inserted. But now we are making some changes here. We are saying not 0, but whatever was the sign, that same sign bit will be inserted. If it was negative, 1 will be inserted. If it was positive, 0 will be inserted. Right? So this is denoted by 3 greater thans. So here you have an example, data arithmetic shift by 2 positions. Well, here exactly this thing is available in a language like C. You have a to the variable A. If and you have something called concatenation operation, where suppose A was a 4-bit vector, B was a 3-bit vector. So what would be a single bit vector? The behavioral description of an 8-bit adder. Cout comma some concatenation, which means the left hand side is a concatenated item which represents precedence values. So this is lowest priority and this is highest. B and so on. There are several others. Okay, let's see. So in Verilog, the operators that are supported are as follows. So you have two unary operators, one is plus, one is minus, and among the binary operators in curly bracket. This will mean repeat 5-bit vector f2 is the operator precedence. This chart actually shows you just overall picture how the precedence varies. So this is lowest priority and this is highest priority, and means operators on the same line have the same precedence, and excepting the last operator, the conditional operator. So all other operators, they are left to right associative. Means suppose I write a plus b plus c, in fact, then the shift operators, then the relational operators, and relation operator less than operations. So among the just arithmetic operations, you have exponentiation in the highest, then comes the other operators, multiply, divide, mod. Well, here I have not shown, then will come addition, subtraction will be there, so I have not shown all the operators in fact. Then the shift operators, then the relational operators, and relation operator less than, greater than are the higher priority, and equal to, not equal to checking will be lower priority. Then comes the bitwise operators, and is the highest priority, then XOR, then OR. This is what the priority value. Now, when you specify this, this means you check for equality following a rule like this. Suppose I am checking two numbers a and b is 1 0 1 be compared, then this means exact equality. So if a is 1 0 1x and b is also 1 0 1x, then only this equality will be returning true. Okay, you recall that in Verilog we have a 4-valued logic system where the logic values supported are 0 1 don't care or undefined and high impedance z. So if you write triple equal to, then these values are matched in an exact way, x and x, z and z, 0 and 0, 1 and 1. But if it is double equal, then it is not done that way. Okay, this is just the only difference, right? So these are a few things which I have already mentioned, most of them. And the first point is a little different. Let's say when you are using an arithmetic expression, let's say we are using a and b, two numbers, we are adding a plus b. Let's say a is a vector, b is also a vector. Suppose for one of the number, let's say a, one of the bits is having a state x. So when you do the addition, the entire sum will become x. This is the rule of arithmetic operation. Okay, so the presence of either an x or a z in any variable which is used in an arithmetic expression will result in the value of the whole expression to become unknown x. So all the bits will become x. And this I mentioned, logical operators generate 1 bit result, relation operators also generate 1 bit result, false is 0, true is 1. Okay, so with this we come to the end of this lecture, where we have tried to summarize the various kind of operators, the topics that we have discussed during our last few lectures. We have talked about the various constructs of the Verilog language. We had looked at some of the fundamental constructs, the operators, how we can frame the expressions for evaluation, and some of the operations we have defined for assignment, for example using the assign statement. There are a few more which we will be discussing in the due course of the lectures, but what we are trying to deal with in the present lecture is we shall take an example, and with the help of an example we shall try to illustrate a few points and concepts which are considered to be good design practice when someone is going about designing a digital system using a hardware description language. So the topic of our lecture is Verilog modeling examples. Now actually what we are trying to do here, let me try to explain this first. You have seen that when we model some system using Verilog, broadly there are two fundamental ways of doing it. So we call it behavioral and structural modeling. You can do either using behavioral or using structural. Now in the example that I shall be giving in this lecture, we shall be just elaborating on this further. Now just to tell you about, when we talk about behavioral modeling, what we are actually doing, we are actually saying that how a system is working. We are not telling or talking about how it is actually constructed or is to be constructed. We are saying that, for example, I have an adder, the sum output should be a XOR b XOR c, the carry output should be ab or bc or ca. So I am not telling that whether you will be using AND gate, OR gate, NOT gate, or NAND gate, or XOR gate, what, or how you will be interconnecting them. So if I say just the behavior either in the form of this expression or in the form of a truth table, let's say that is a so-called behavioral expression which is much easier to do. So when you are a designer, when you have something in your head, in your mind, you are trying to design something, so the first thing that you can write or start with is a behavioral description of your model or your thought process, what you are thinking about. Now once you have thought about the behavior, now we can think about how we can implement it. Okay, let's take that same example of a full adder. So once you have thought about what is the functionality of a full adder, now you think about how you want to implement it. Now you may see that, well, I want to implement it using a technology where you have only NAND gates. So let us not use AND or NOT operation. So all the AND or NOT, whatever is there, we will be translating them using De Morgan's law, using NAND operations only, and we will be implementing it using NAND. So just in this diagram, so as I said, behavioral description is often the starting point, because it is easier to write a Verilog module in the behavioral. But structural description, this is more with respect to hardware implementation. Like here I can say that, well, to implement the carry output of the full adder, let's say to implement carry, I need, I'll say that I'll need 4 NAND gates, let's say. So, and I'll also tell how the NAND gates are interconnected. I'll say that, well, you interconnect the NAND gates like this. There will be 3 2-input NAND gates and 1 3-input NAND gate. This will be AB, BC and CA, and this will be your final carry output. So this is what is your structural representation. You specify some modules and you also tell how they are interconnected. Now obviously this is much more detailed. So when you are thinking of the behavior, you have not yet thought about these gates and how they are interconnected. Okay, so there will be a process that you will have to go through, that from behavioral to structural you will have to make a translation, right? So the normal design process is that we start with a behavioral description. Now in our behavioral description, our total description may consist of 1 or maybe multiple modules. Let's say 1. We systematically try to convert them into structural descriptions. There can be several steps. I shall take one example and I will show you that how we can use several steps in the translation and how you can carry out some kind of a hierarchical design process in order to achieve it, at the end of which you will be taking the example of a 16 16:1 multiplexer and illustrate some of the points I have just discussed. Number of select lines, number of input lines. Then we shall be implementing complete hierarchical lines that we are using, 4-bit select line, test it whether it is working correctly or not. We write a test bench. Just go back. We have a module like this, mux 16:1, where there are 3 parameters: input, select, and output. Okay, and now just we want to verify its operation through simulation, and we have written a test bench for it. So what is our test bench looking like? Let's say here we have instantiated our multiplexer, mux 16:1. You see, this was mux 16:1. The parameter names are in, cell, and out. So we are using this notation to specify the parameters: dot in, dot cell, dot out. And in this module, the corresponding variables are a, s, and f. And in order to express the data types, we specify a and s as reg, because they will be appearing on the left hand side. They have to be of type reg, and f is of type var. This a is 16-bit, s is 4-bit. So the test bench, what I'm doing, you recall, we'll be just looking more formally into the constructs of a test bench later, but let's illustrate with examples. This initial block I'm repeating, this means that we execute this begin end block only once. That is the purpose of the test bench. You will be testing your module once. Whatever you have specified, those values will be applying to the inputs, and you will see what the outputs are coming. Okay, that is the purpose of the test bench. So just ignore the first 2 lines once more. We'll again come back and explain this once more. Well, this line, monitor. Monitor, we are monitoring a few of the variables. $time is a system variable that indicates the simulation time. And then in a C-like notation, we are saying that we want to print the values of A, S, and F. H is a hexadecimal specifier, H, and F is a single bit. I give it B. B means byte. Then only you print. You do not print at every time, 1, 2, 3, 4. Don't continuously go on printing. Now I specify the inputs. So what I'm saying is that at time 5, I apply hexadecimal value, 16-bit hexadecimal H, 3F0A. So let us write down here also 3F0A. What does 3F0A mean? Let us write it down. 3 means A is 1, 0, 3F0A. So index 8, 9. Think of a multiplexer, and you're getting the output F here, right? So select line will be selecting one of these bits, and that bit will come out. All 0 to S. So let's see what will happen. So if we apply select line, right? This bench, what we do? Well, we wait for another time 5. After delay of 5 again, we set S to 1. 4 hexadecimal, value is 1. So, okay, what is your 6? S is 6. 6 is here, so this is 0. So you'll be getting this value 0. Now this will happen at time 15. And the last one, you apply. I told you earlier that you can use any of the simulators to simulate these, and I had suggested to use the iVerilog one, which is very easy and it is freely available. So here in the examples that I am showing, I have used iVerilog and GTK Wave to show you the simulation outputs. Okay. So if I just simulate it using iVerilog, so I get an output as is shown in the window here. Monitor means whenever any of the variables that we execute this big cell dot out, and in this module, behavioral modeling of this multiplexer. Okay. Now how do we test it, whether it is working correctly or not? That I am showing, I have used iVerilog and GTK Wave to show you this for your reference. A. Now the first 2 lines in the initial statement, I am repeating this, I mentioned this earlier also. See, these variations with time, this information you can also dump into a file, VCD. Okay. So here I am giving a name, mux 16:1 VCD, variables which are instantiated in like this. So you see the font size is a little small, but you can decode. See, on top the time is mentioned. Just going back, at time 5 the values are starting to change, right? So you see this is 7, this is 14, 21. So 5 is here. This is our in, select, and out. So in was initially XXXX, select was out, select was X, out was also X. So it starts getting selected here. 3F0A, this is the value I have applied. Select, initially you have applied 0. So the output you are getting 0, 0 level. Then select you have given 1, so output has become 1. Then select you have given 6, output has again become 0. Then you have given C, graphical form, and the shown a very simple behavioral description of a multiplexer 16:1. I have shown how to write a test bench, and I have shown you the simulation results. Now what I will do, I will proceed with our so-called hierarchical refinement. We shall be modifying our module description, but we shall be keeping our test bench the same. We shall not be touching our test bench. We shall be making modifications. We shall be again running the same test bench and verify whether the simulation results that we are getting is exactly the same as what we got here. That should be so, because the result should conform to us exactly that. So this is the mux 16:1 description, input, output, and we have defined this wire T, T0, T1, T2, T3. So these 5 multiplexers we have instantiated. Just check for M0, we have in 320 and select 120, output is T0. Let's see. For M0, input is in 320, in select are cell 0 and cell 1, and output is T0. Okay, same thing. Similarly, M1, M2, M3, and finally M4. The input is T. You see, input is T, T0, T1, T2, T3. You can simply write T. It's a vector. The high order bits of cell 3 and 2 are this description of a 16:1 mux. Next, we proceed one step further. Now we are three 2 to 1 multiplexers, you can implement a 4 to 1 multiplexer. So 2 and 2 inputs get here, the least significant select line will be here, most significant select line will be here. So that way, same way, mux 4 to 1 I can use by instantiating 3 copies of mux 2 to 1. I am still defining in a behavioral fashion. 2 to 1 mux, I do this. So at the last step, implement it using structural fashion. So a multiplexer, how do you implement a 2 to 1 mux? You can take this in 0 can be connected here, this in 1 and through an inverter here. This in 1 this and is the typical design flow of a designer. So when a designer goes about designing a complex digital system, well, I have shown a relatively very simple example so that working out another example. See, working with examples is good in two respects. One is that it can give you confidence in actually learning about the language and how you can approach the design of a thing, and secondly, you can actually understand the flow, the design flow, how it is actually done in practice. So the second example that we will be taking is a slightly more complex example than the multiplexer we took last time. This is the example of an adder. Select line will be here, most, but again this mux 2 to 1 I am still defining in a behavioral fashion. 2 to 1 mux I have just defined it like this, where select is a 1 bit and input is 2 bits. Okay, so I proceed like this. So at the last step I have the smallest So in this lecture we shall be working out another example. See, working with examples is good in two respects. One is that it can give you confidence in actually learning about the language and how you can approach the design of a thing, and secondly, you can actually understand the flow, the design flow, how it is actually done in practice. So the second example that we will be taking is a slightly more complex example than the multiplexer we took last time. This is the example of an adder, and it's an adder circuit which is part of an arithmetic logic unit, ALU. So this is our lecture topic. So we describe an adder. Again, we start with the behavioral description of an adder. Now let us see that what we are trying to do here. Now this adder is just symbolic as an example we have taken, but in general let us call it, this is an arithmetic and logic unit, but in the code that I will show we will only talk about addition. So what does the ALU do? The ALU will take two data as input, let us call them x and y, and it will be generating a result, let us call them as z as output. So the example that I will be illustrating, I shall be only talking about looking at our sign 0. The result means after addition I have done something which is not fitting, there is an overflow. So what are the parameters? The name of the module we have given the ALU x, y, z, x. X and y are the inputs. Let us assume they are 16-bit numbers 0 to 15, 0 it is positive. So the MSB of the result z, that will go into the on z, that will be 0, and parity. Now here this means that either both x15 and y15 were 1 and 1, this is dot means AND operation, plus means OR operation. x15, y15, z15 bar, which means this is 1 and this is 0. So the numbers were negative. After addition the number has become positive, which is never possible. This is possible only when overflow has taken place. Or the reverse condition, this was 0, but in this sum it has become 1. The numbers are positive, but the sum is showing as negative. So if you implement this logic, that will give you the overflow straight away, right? So here we have done exactly that. We have used this same expression to generate the overflow straight away, right? Or the reverse condition, this was 0, but in this sum it has become 1. The numbers are positive, but the sum is showing as negative. So if you implement this logic, that will give you the overflow straight away, right? So here we have done exactly that. We have used this same expression to generate the overflow, right? So this is the behavioral description of the adder. Now just like in the example we showed earlier, we have also written a test bench here. So we call it as YOou test. In the first step we have given the first number x equal to 16-bit hexadecimal 8FFF and y equal to 800, x is EDEF, so FFFF, right? So this should be the sum, and of course the flags will be set. Let's see. So if you just simulate the simulation of 0000 FFFF, so this is exactly what we got here, 0FFF, 000 FFFF, and in all cases you can verify the sign 0FFF, the sign is positive, 0 0 this is also. So here you can all check the signs here, 0 flag, carry flag, parity flag and the overflow flag. You can check all of them, they will be consistent. Okay. So this is our simulation output with respect to the description which we have given here. So it works correctly. Now what we are trying to do here, we have just given a behavioral description of a full adder, of an adder. Now this we want to refine into more detailed description. So the first step what we do, is we had started with the design of a 16-bit adder, right? So what is, so they will be all fed with 2, right? So this is our same thing. So this is x, this is y, sum is z, you can see the value. Just implement here, the carry out is C2, for the next adder C2 is the carry in, sum. But the 4-bit adder still we are leaving it in a discrete, next stage is that we are using 4 full adders. So this is exactly what we have done, listening to what I am saying, but also this full adders also you can implement using structural way, because you see this is one implementation of a full adder, which is a compact implementation which requires a total of 5 gates. One S1 AB, it means this is G1, S5, this is G5, C2, 16-bit adder where the individual 4 look ahead adder. So in the next design, here we shall, or here we are looking at a design of a 4-bit adder, adder 4, using carry look ahead principle. Now here let us skip this, we shall come back here. Before explaining this description, let us first look at how a carry look ahead adder works, okay? Because this will be required to understand how we have come up with these expressions, because these expressions may look a little complicated, okay? So you see, for a replicatory adder, that means as you have seen, the total propagation delay will be proportional to the number of stages n, because as I said, the carry ripples through from one stage to the other. So carry look ahead adder is one way to speed up the addition, where the carry signals are generated in parallel for all the various stages. So effectively, the addition time reduces from order n in replicatory adder to order 1, which is a constant time in carry look ahead adder. But the flip side is, the drawback is, the hardware complexity also increases very rapidly with the number of bits n, okay? Let's see how. Well, if you look at a single full adder, so in a replicatory adder, you look at the ith stage full adder, where the inputs are ai, bi and ci, the output is a sum si and a carry si plus 1. Now we are defining 2 signals, or you can say 2 functions called carry generate and carry propagate. Well, carry generate specifies the condition where a carry is generated in the full adder irrespective of the carry in. The condition is, whenever both the data inputs ai and bi are 1, then carry will be generated irrespective of ci. So that is gi, gi is ai and bi. And propagate, carry propagate represents the condition. It says that when the input carry will be propagating to the output, what is that condition? The condition is, among a and b, at least one of them, means exactly one of them should be 1 and the other should be 0. Suppose it is 0 and 1, then if there is a carry coming 0, 1, 1, that will generate a carry, the carry will be propagating. So this is the condition for carry propagation, exactly one of a and bi should be 1. So this carry propagation is defined by the exclusive OR function. This is generate and propagate. So gi and pi you can implement by an AND gate and an XOR gate, right? Now with this you can write that the output carry expression, output carry will be given by, well, either the carry is generated or the propagate condition is true and there is an input carry. So ci plus 1 you can write down as by an expression gi or pi ci, okay? Now this you can use recursively to find out an expression, ci plus 1 equal to gi plus pi ci. So you can write this ci, you can write as gi minus 1 plus pi minus 1 ci minus 1, you can expand it like this. The ci minus 1 again you can write as gi minus 2 plus pi minus 2 ci minus 2, like this you can recursively go on expanding, okay? So I am not showing you the whole thing. See, basically what it means, I am just writing down some simple expressions. See, what you got is ci plus 1 equal to c1 as this c1 c2, so g1 plus p1 c1, right? Now c1 you have already got this, so you can substitute c1 here, so this becomes g1 plus p1 multiplied by this, so p1 g0 plus p1 p0 c0. You go to c3, c3 will be g2 plus p2 c2. Now c2 you have already got this, so this will be g2 plus p2 multiplied by this, multiply this, p2 g1 plus p2 p1 g0 plus p2 p1 p0 c0 and so on, like this will be getting the expression. So you see, all the carries you can get just by a 2-level AND OR kind of expression. There is no question of carries rippling through, but as you go on, these expressions become more complex, bigger expressions, more number of gates, okay? This is what I am saying. So actually this is what I have just now showed. C1 is this, C2 is this, C3 and C4. So you require so many gates, and sum you can directly generate. You see, P is nothing but A and B's XOR. So the sum is the XOR of all the 3 bits. So you can simply write P0 XOR C0. Similarly, S1 is P1 XOR C1 and so on. You need 4 XOR gates. So in a carry look ahead adder, carry look ahead, you have a circuit first which generates all the G and P's, which means XOR and AND gates. Then we have a carry look ahead circuit which implements these functions C1, C2, C3, C4, okay, using AND OR circuits. So it generates C0, C1, C2, C3 and also C4. So now you can directly generate the sums by using XORs. XOR the carry with the P's. So the total time is constant irrespective of the number. Okay, there is no ripple of the carry. Okay, so this will be much faster. So just remember these expressions and the sum expressions. So if you remember these expressions, you can just correlate that what we have done is exactly that. Here the carry propagate and generate signals I have defined as wires in between, and the intermediate carries also. So P0 is A0 XOR B0, P1 A1 XOR B1, and so on. Similarly, the generate signals and A0 and B0, A1 and B1, and so on. So I generate the propagate signals, I generate the carry generate signals, then I generate all the carry signals. C1 equal to G0 or P0 Cin. Cin is C0. You see this expression? C1 equal to G0 or P0. This C0 is Cin. C2 is G1 P1 G0, P1 P0 Cin. Exactly we have it. C4 is finally Cout. So as you can see, as the number of bits increases, these expressions are becoming more complicated. And finally, sum is the XORs. So this is a carry look ahead adder. So in the same way as I said, you can replace a module by a better or an improved module. You replace a module by another module. Like for example, we replaced a 4-bit carry look ahead adder by a 4-bit ripple carry adder by a 4-bit carry look ahead adder. We have got a faster adder, but we can do simulation and you can find out that functionally our design is correct. It is working correctly. So this actually completes our discussion for today's lecture. See, what I tried to illustrate over the last two examples we discussed is that when we look at non-trivial designs, slightly bigger designs, we often break the design up in a hierarchical fashion. Whatever something was discussed in a or described in a behavioral fashion at one level, we do some kind of iterative refinement. We break that behavioral description into structural description, try to be more detailed, and we repeat the process until we reach a point where our entire design becomes structural. So in a normal digital system design, you will see later that, well, we do not only have combination circuits, we also have sequential circuits, flip-flops, state machines, and so on. So we shall see later that when we have such a system where we have combination circuits, registers, and also a lot of finite state machines, there it may not be worthwhile to convert all the modules, all the descriptions into structural. Well, the data path, the circuits where the actual calculations or computations are carried out, those of course we can, it may also have sequential the problem described in a behavioral fashion at one level, we do some kind of iterative refinement. We break that behavioral description into structural description, try to be more detailed, and we repeat the process until we reach a point where our entire design becomes structural. So in a normal digital system design, you will see later that, well, we do not only have combination circuits, we also have sequential circuits, flip-flops, state machines, and so on. So we shall see later that when we have such a system where we have combination circuits, registers, and also a lot of finite state machines, there it may not be worthwhile to convert all the modules, all the descriptions into structural. Well, the data path, the circuits where the actual calculations or computations are carried out, those of course we can convert into structural fashion, but the controller, the circuit which implements a finite state machine which generates the control signals, often that we do not convert into a structural fashion because it involves too much of a work on the part of the designer. So we shall just learn these things slowly over the next lectures. Thank you. In the lectures that we have seen so far, we have looked at a number of examples where we took some modeling instances and showed how we can create the description using Verilog. Now in this lecture we shall be starting our discussion on the various ways in which we can model or create the description of. So broadly speaking, there are two different styles of description. I have already given you some examples of these, so you have seen some examples, but broadly speaking the description styles can be categorized into two different types. Okay, the first one is the so-called data flow description style, which uses continuous assignments using the assign statement that you have already seen in many examples. So this uses such kind of assignment statements using assign. Now as an alternative, you can have behavioral design or description styles as well, where you use some kind of procedural statements which are somewhat similar to a program in a high level language that you sometimes write. You see, whenever you write a program in a high level language like C or any such language, you try to specify what you are trying to do. So in that statements which is similar, we shall be discussing these for completeness. Let us also look at it once more. So the data flow design style is identified by the keyword assign. So whenever you want to make some assignment like a equal to b plus c or sign equal to z15, bit number 15 of a vector z, we use this keyword assign before that. Now I mentioned earlier also, whenever we use an assign, this forms a static binding. It is not that whenever the statement is executed, b plus c is computed and the value is stored in a. Not like that. Whenever you write a equal to b plus c, something like this will be happening. Let's say b is a register, c is another register, So there will be an adder which will be generated, net which you are calling A. This A is not a register, it is just a net. So whenever either B or C will change, this A will change immediately after the delay of this adder. Okay? So there is no concept of any clock or anything. Such an assignment, we said earlier also, is referred to as continuous assignment. Right? Okay. So there are some constraints in such assignment statements using assign. First thing is that the left hand side must be a net type variable, typically a wire. But however, the expression that we are using on the right hand side here, B plus C here Z15, these expressions may consist of variables which can be either net or register or any combination of the two. And this is called continuous assignment because this is continuously active. There is no signal that tells you that when this operation will be carried out and when the output will be stored in that target. So it is not like that. It is some kind of continuous assignment. Whenever one of the input changes, the output net value will be changing or be affected right away after the necessary delay of the circuit. Okay, fine. So these kind of assign statements, typically we use it for modeling combinational circuits, but we shall see that we can also use this for modeling sequential circuit elements, which are of course not very common, but we can also do this. We shall be taking some examples later. Right? Okay. Now in a Verilog module, we can have any number of assignment statements, assign statements, and this is a very typical structure. So whenever we write a Verilog module, let us say this is a Verilog module. It starts with the keyword module, it ends with end module. So in the beginning, we typically start with the signal declarations. All the net and the register type variables are declared there. Then after that, we usually club all the assign statements together. This is the normal practice. And then the other kind of statements will come, which you shall see later. Right? This is how a typical Verilog module structure look like, where the assign statements are typically placed in the beginning, right after the signal declarations. And another thing I also mentioned, that in the assign statement, we just tell or say what we are trying to do. Suppose we write A equal to B plus C, we are just saying that we want to add B and C, and we want to store the result back in A. But we are not telling what kind of adder to use, how to add, and so on. So this is more like a behavioral description. Okay, we are specifying the behavior, but not the exact structure of the circuit. Okay. So now we shall see a number of examples, typical usages, and while we are going through the examples, we shall also learn about a number of things there. Fine. This is one very simple example. We saw an examples of multiplexers earlier. So here we are generating a mux. Like whenever we have a module description like this, now see, now right here we are not talking exactly about simulation. We are talking about what will happen when, let's say, we are using a synthesis tool to synthesize our circuit. So for that purpose, what will happen? How the synthesis tool will be carrying out synthesis and what kind of hardware blocks or modules will be generated. So let us see this example. So in this example, you see that we are using a module called generate mux, which has 3 parameters. The input is a 16-bit quantity, it is a 16 to 1 mux, 4-bit select line and a single bit output. So we are simply using a single line description which says assign out equal to data of select. So data is like a vector, 16-bit vector, select is a number, 4-bit number which selects one of the bits, and that particular bit goes to out. So which is what mux is. Now whenever the Verilog synthesizer encounters such a description, a multiplexer will be generated. So how does the synthesizer know that a multiplexer will be required to be generated? The keyword is a non-constant index in the expression on the right hand side. So whenever there is a vector which I am using with a non-constant index, select is a variable, right? It is not a constant. So the index value is a variable, then we will be generating a multiplexer. Okay? So the data, whatever is there, that will be the input to the multiplexer, and this variable will go to the select line, and this out will be the output point. Now the point to note is that, like as I said with the example I have shown, that whenever there is an array reference with a variable index, the multiplexer will be generated. But however, if on the right side it is not a variable, it is a constant, let's say like this, assign out equal to data 2, then no multiplexer will be generated, because you see data is nothing but an vector. Okay, vector means a collection of bits. So it is a 16-bit vector. So the index values will go from 0 up to 15. So when we say assign out equal to data 2, what will happen is that data 2 is this bit. This bit will straight away be taken out, and this will be called as out. So no circuit will be generated, it will be just wiring. This particular bit will be connected, or it will be given a name out. Okay, this will be what will happen if I give an assignment like this. No gates or no hardware blocks will be generated for an assignment like this. But if I write, like in the previous example, assign out equal to data, but I give a variable cell here, I do not know which bit I want. So here you need to synthesize or generate a multiplexer where the input will be your data, this will be your select lines, and on the output side you will be getting the output bit out. Right? Okay. So let's take another example. Here, this is also an example for multiplexer, but we are using a conditional operator here. You need to synthesize or generate a multiplexer where the input will be your data, this will be your select lines, and on the output side you will be getting the output bit out, right? Okay. And on the output, but the point to note is that, like as I said with the example I have shown, that whenever there is an array reference with a variable index, the multiplexer will be generated. But however, if on the right side it is not a variable, it's a constant, let's say like this, assign out equal to data2, then no multiplexer will be generated, because you see data is nothing but an vector, okay, vector multiplexer, but we are using a conditional operator here. So what we are doing, let's try to understand. This a and b are two 4-bit vectors, so the index goes from 0 to 3 in this order we have said. Similarly, f is another 4-bit vector, which is the output, and cell is an input. And in this conditional operator we are saying that if cell is true, cell is a 1-bit vector, if this is true means it is 1, then you select a, else you select b. Select a means a will be assigned to f, otherwise b will be assigned to f. So actually what will happen here, this will be generating a multiplexer, means every conditional operator will be generating a multiplexer because it is if then else. But here this a and b are both 4-bit vectors, and f is also a 4-bit vector. You see, whenever you have a conditional thing, what you are doing, you are checking for a condition. If the condition is true, you are selecting one. If the condition is false, you are selecting the other. So what you are actually generating is a 2 to 1 mux. You will be generating a 2 to 1 multiplexer. But here what has happened in the example that I have given, both a and b and f, they are all 4-bit quantities. So actually it will not be one 2 to 1 multiplexer, but 4 such multiplexers will be generated. So each of them will be having 2 inputs and 1 output. They will be having a common select line, SEL. This will be connected in parallel to all of them. Now the inputs will be connecting for the first one A0 and B0. The second one will be connecting A1 and B1. Third one will be connecting A2 and B2. And fourth one we are connecting A3 and B3. And in the output side, this will go to F0, this will go to F1, this will go to F2, and this will go to F3. So you see, a statement like that using conditional automatically generates an array of multiplexers like this, and these multiplexers will all be 2 to 1 multiplexers, right? Okay. So here the point to observe is that, so whenever you have a conditional expression like the one we have seen, we have shown in the right hand side, automatically a 2 to 1 multiplexer will be generated. Now in the example which I have shown, because a, b and f are vectors, so it was not one, but an array of 4 such multiplexers were generated. Now let's take an example. Suppose I have given an assignment statement like this. So what will be the hardware this assignment statement will be generating? Let's try to work this out. So our statement that we have seen is assign f equal to, this is a conditional. So the condition checking that we are doing is a equality to 0. If it is true, c plus d. If it is false, c minus d. So this is what we are actually trying to do. Now let us see. So here what will happen? Here there will be a multiplexer which will be, I am just showing one multiplexer, but actually it will be not one but several multiplexers. I am using the array notation. 2 to 1 multiplexers using the array or the vector notation. So it will be having 2 inputs. These are not single lines but multiple lines. Similarly, it will be having an output, not one, multiple. So in the select line, we will be comparing a with 0. So there will be a magnitude comparator. So I need a magnitude comparator circuit which will be taking a as input. It will be comparing it with the number 0, and the result of the comparison will be fed to the select line. So either this will be true or this will be false. And on the other side, I use an adder where I have fed the numbers c and d. The sum I am connecting here, and I also have a subtractor where again I have fed the number c and d. This I am connecting here. So this will be the kind of circuit that will be generated. Now let's say if this adders, let's say this is all 16-bit operation, these numbers are all 16 bits, then actually this is a vector kind of notation, the output is f. So actually it will be not one multiplexer but 16 such multiplexers will be generated, one for every bit of this data. There are 16 bits, so 16 bits have to be multiplexed, so I need 16 2 to 1 multiplexers, right? Okay. So let's take another example. This is the example of a decoder, means this is an example which will be generating a decoder. So here you see what we have given. Here we have one input, in is a single bit input, select is 2-bit vector, and out is a 4-bit vector. And what we have written is something like this: out with an index of variable equal to in. So now the array access with a variable index is appearing on the left hand side. So whenever such a thing happens, a decoder will be synthesized. So if we have on the left hand side a non-constant index select, then a decoder will be generated. So what the decoder will do, the input value will be going to one of the outputs. Okay. So let's take another example. This is the example of a decoder, means this is an example which will be generating a decoder. So here you see what we have given. Here we have one input, in is a single bit input, select is 2-bit vector, and out is a 4-bit vector. And what we have written is something like this: out with an index of variable equal to in. So now the array access with a variable index is appearing on the left hand side. So whenever such a thing happens, a decoder will be synthesized. So if we have on the left hand side a non-constant index select, then a decoder will be generated. So what the decoder will do, the input value will be going to one of the outputs, and this do, okay, this E will be in capital, we don't care, irrespective of D, one will become 0, that will depend on the relative delays of these two gates. Which one is faster, that will force the output to it to change first. Okay. Testing, we also wrote a sample test bench for this. To check whether this latch is actually working like a latch should work, we wrote a test bench like this, where this SR latch was instantiated, we call it LAT. So this S and R, which are the inputs, were declared as reg, and Q and Q are the outputs, were declared as wire. So the output should become, Q should become 1, then 1 and 1. Then just for testing, we applied the invalid condition 0 0 followed by 1 1 to see that what the simulator does here. So what the simulator did was something like this. First few lines was absolutely perfect, what we expected. S0 R1 generates Q0 and Q bar circuit operation. That the data flow or the continuous comes in two flavors, and you have already seen some examples using these. These are sometimes called
Wenn Ihr Flug verspätet oder annulliert ist, stehen Ihnen
sound, make it loud, be a clown for you, or maybe we could be a Romeo and Juliet, except without the age difference, and we can forget the death. Cause this is love at first sight, there's no doubt in my mind. And darling, forget about the time, cause you're mine. And I'll spend every second chilling with you. Like this, that vintage Nickelodeon innocence love. Innocence the type of if we fight, let's chill and make up. You're one in a million pay stubs, but to me, you're like a lottery. There's a lot of fish in the sea, but you're a catch that's so startling, baby. I know that there's a lot to do, it's awful too. And in your past, there's a lot to chew. I'll buckle up, like your burden's a weight to carry, but it lessens at a steady rate. And I'll be by your side like your phone pocketed on second dates. Honestly, I just want some acknowledgement for confidence and compliments, but maybe I'm not hitting the dot, but I'm still taking my shot. I'ma practice and go again, and you can show me around, and you can even will your friends. Like I know that they'll be talking with their dissonant whispers, but shiver me timbers if they can rock the relationship. Do you know who you playing with? I'm feeling like Midas, but you was gold to begin with. I didn't help in the slightest day.
My day needed.
Of course he's gonna hang around for more. It's sort of like a drug. It's addicting.
And ooh, girl, I'm addicted to you. You're my dopamine and joy. Make me forget and then act coy. Oh, ooh, girl, let me know what to do when I'm just thinking of you. You're the one I'm addicted to. Yeah.
All of these subscriptions can really add up. So, why not get YouTube Premium? It's like having all those and the entire world of YouTube uninterrupted for only $129. YouTube Premium. Try 1 month free. YouTube Premium is ad-free YouTube and YouTube Music Premium. Try 1 month free.
Procedural blocks, they come in two different types. One is the initial block, other is the always block. The main difference between these two are the initial block is executed only once, and this is used exclusively for writing test benches or test harnesses, and these are not used in synthesis. When your objective is to synthesize the circuit, you should not use the initial construct. Initial construct is to be used only when you are writing the test benches. It is executed only once at the beginning of the simulation. And the other type is called always block. Well, this always block can be used inside the test bench, or it can also be used inside your circuit description module. This is like a continuous loop which never terminates. You see, the always block models a hardware circuit in a more natural way. Whenever we design a hardware, that is supposed to work as long as power is switched on. Okay? So we cannot say that this hardware circuit will be working for 10 seconds and then it will automatically stop. It will not stop unless you explicitly send a signal to stop it. Okay? So the always block is like a piece of hardware which is taking some input, generating some output, and continuously it is doing it in a repetitive fashion. It never stops. It is more like working in a continuous loop. Now, these are called procedural blocks, initial or always. Now, inside the procedural block, you have some code which comprises of a set of sequential statements. Sequential statements means they execute in the order they appear or they are written one by one. Okay? So, let us see. First, the initial block. Well, we have already seen some examples of the initial block. We have seen some test benches. We shall see some more complex test benches later again, but at least whatever we have seen, so you can appreciate that the statements that appear inside the initial statement, that is referred to as the initial block, and they are typically grouped between begin and end. So, inside an initial block, it comes like this. When you give initial, this is a statement. So, inside it, the statements are grouped in begin and end, and this is what is defined as a initial block, right? Okay. Now, the rule for execution is that the statements that are there inside this begin end, they start executing at time 0 and they execute only once. This is important. So, if you do not specify any explicit timing by giving that hash command, it is assumed that the first statement inside that block will start executing at time t equal to 0, and initial means the statements will be executing only once. Okay? Fine. And in a typical test bench, there can be multiple initial blocks, and if there are multiple initial blocks, then all the blocks will be executing in parallel concurrently, and all of them will start at time t equal to 0. This is something you should remember. Now, as I have said repeatedly, that this initial block is used to write test benches, but sometimes when you are trying to see how some typical Verilog constructs are working, you can also use initial block just for testing. You can do some computation, you can give a display on a monitor statement to print it just to see whether it is working or not, but not for synthesis. When you are designing and your target is to generate the hardware, you can forget about initial. Initial is something which you should not and cannot. Not use. Okay, fine. So, this initial block is used for writing the test benches. The test benches, as you have seen, they basically specify the stimulus or the inputs that are to be applied to your design, whatever you have designed, and also it specifies how the output of your design are to be handled, whether they are to be displayed or they are to be dumped into a file so that you can display the waveforms later. Okay, this test bench specifies all these things, and they are typically done inside always blocks. Always means initial blocks. So, some simple example. So, this is the example of a test bench, but I am not instantiating the module because our objective is just to illustrate the initial blocks. Here you see we have used 3 initial blocks, and if there are multiple statements inside an initial block, you need this begin and end. but if there is a single statement, you do not need the begin and end, it is optional. So all the three initial blocks, they start execution at time t equal to 0. You see what is happening at t equal to 0. Okay, this is something like a full adder. You see the names are quite familiar: a, b, carry in, sum and carry out. So I am initializing with the carry in as 0, and in the other initial block, which also starts at time t equal to 0, it encounters a delay of 5. So it waits for 5 units, and then it applies a equal to 1 and b equal to 1. Then it again waits another 5 units and then applies b equal to 0, and that's it. This is a single execution. And the third initial block, this also starts at time t equal to 0. It waits for 25 time units and then calls the system function finish, which means the end of simulation. So at time t equal to 25, the simulation will stop. So such multiple initial blocks are very typical inside a test bench. Now inside a test bench, you can also have always blocks, as we shall see later with some examples. Okay. So as I have said, to summarize, the three initial blocks execute concurrently. The first block, because there are no delays, the statement executes at time t0. The third block calls finish, so it terminates simulation at time 25. Okay. Now just to note that there are some shortcuts in declarations which are supported by Verilog. Means at least the recent versions of Verilog which are available now. Now see, normally whenever you have some parameter in a module which is an output and which is assigned inside a procedural statement which has to be a reg, you declare it like this: output, let's say it's a vector 720 data, and again you have to give reg 720 data to indicate that this data is also a register type, so that it can be assigned inside a procedural block later on in the code. But Verilog now permits us to combine these two statements in a single statement like this. You can straight away write output reg 70 data. So you are specifying two things together, that data is an output and also it's a register type variable. Okay. Secondly, see, earlier you used to write something like this, say a clock. You declare a clock as a register type variable, then in initial block you initialize clock to 0. Suppose this is the single statement inside the initial block. Now this initialization and declaration can be done together in a single statement now. You can write something like this: reg clock equal to 0, because here also you see clock equal to 0 initialization will take place at time t equal to 0 because no delay is specified. Same thing will happen here. Whenever you are declaring clock at time t equal to 0, it is also initialized. Okay, fine. Now let us come to the always block, the other kind of procedural block. Now there is a statement, the always statement. Just like we said that there is an initial statement and it comprises an initial block, in exactly the same way there is an always statement. Inside the always statement, typically you have begin end again. So begin end can group several statements together, and this whole thing is called a always block. Right? Okay. So the set of statements which are behavioral statements inside the always, they constitute the always block. And as I have shown in that example, this block is grouped using begin and end. Now just like initial, this always block, the statements inside it also starts at time t equal to 0 and executes the statement inside the block repeatedly and never stops. What I mean is that here inside this always block I have this begin end statement. There can be several statements here. Now these statements are executed repeatedly in an infinite loop kind of a thing, and it never stops. Initial executes only once, it executes once and stops, but always will never stop. It will execute the block repeatedly in response to some event condition that I will mention very shortly. Okay, this is the difference. So the always block is typically used to model some activity which is repeated. For example, I have a clock generator. As long as there is power or switch off the power continuously. Well, for simulation purposes, we can specify delays even within always block. But again, when we are actually generating a hardware, the clock generator, this delays doesn't mean it will stop. But in an actual hardware, there are certain things that we cannot do, that we'll see later on. Because you see, you have looked at so many different constructs in the language, something which you can do only for simulation, something you do typically for synthesis. So we shall see later, we'll talk specifically about it. There is a subset of the language, which of course is a little subjective. It can vary from one software or synthesis tool to another. There is a subset which is called synthesizable subset. There is a set of statements or set of features which are only allowed by the synthesis tool. If you allow or use any other construct of the language, the synthesis tool will simply ignore them. It will not take them. Okay, fine. So here is an example, just a clock generator subset. There is a set of statements or to another subset of only for simulation. See, you have looked at so many different constructs in the language, something which you can do only for simulation, something you do typically for synthesis. So we shall see later, we'll talk specifically about it. There is a subset of the language, which of course is a little subjective. It can vary from one software or synthesis tool to another. There is a subset which is called synthesizable subset. There is a set of statements or set of features which are only allowed by the synthesis tool. If you allow or use any other construct of the language, the synthesis tool will simply ignore them. It will not take them. Okay, fine. So here is an example, just a clock generator. So this is just a module, just like a test bench, which is generating a clock signal. This is an output reg. You see, this initial block at time t equal to 0 is initializing the clock signal to 0. So, initialize to 0 at time 0. And in the test bench I can also give an always block. I have given always block which says that with a delay of 5 you use clock equal to not clock. What does this mean? Suppose this is my time t equal to 0 and this is my signal clock. My clock equal to not clock, my clock becomes and the time. And just for simulation we can specify this, that at time always blocks can coexist. You can have a combination of initial and always block, but of course within the test bench only, not within the main Verilog module. And they all execute concurrently. The difference I mentioned, that initial will execute only once, but the always block will execute indefinitely, repeatedly. So, a module in general can contain any number of always blocks. I mean a module where I am describing the hardware, and these blocks are all executing concurrently. Now, I told you just some time back this always block will be executing in response to some event. You see, this is the general syntax of an always block. After always, you give this @ symbol, and within bracket you give an event expression. So, whenever this event expression is sequential circuits, as we will see through examples, clock comes again, it will execute, okay, something like that. Fine, and there are some restrictions here. So, inside the initial or always block, whenever you are assigning some variables to some values, only rich type variables can appear on the left hand side. You can assign values only to rich type variables. The basic reason is that, you see, the sequential always block, as I said, it will execute only when the event expression triggers. Like what I have said is that always @ some event expression, I do not care what it is, what I am saying is that in d equal to b. But now think what will happen during the time when this triggering condition is not true. So, what will happen to the statements? Whatever you have assigned to a and d should remain in a and d. That is why we say that the left hand side must naturally be rich type variables, so that if required, these rich type variables can be mapped to hardware registers by the synthesizer. So, these two statements will execute. But now think what will happen during the time when this triggering condition is not true. So, what will happen to the statements? Whatever you have assigned to a and d should remain in a and d. That is why we say that the left hand side must naturally be rich type variables, so that if required, this rich type v during the equal to, I am right what it is there are some restrictions here. So, inside the initial or always block, whenever you are assigning some variables to some values, only rich type variables can appear on the left hand side. You can assign values only to rich type variables. The basic reason is that, you see, the sequential always block, as I said, it will execute only when the event expression triggers. Like what I have said is that always is like this, a equal to b. So, whenever this event expression will appear or will trigger, these two statements will execute. But now think what will happen during the time when this triggering condition is not true. So, what will happen to the statements? Whatever you have assigned to a and d should remain in a and d. That is why we say that the left hand side must naturally be rich type variables, so that if required, these rich type variables can be mapped to hardware registers by the synthesizer. But it is not necessarily true. Sometimes you will see that the variable may be a rich type variable, but whatever you are mapping, whenever you are mapping it, so it is actually mapping to a combinational circuit. So, no registers or storage elements are required, flip flops, latches are not required. So, a reg can map to either a sequential element or a combinational circuit, but if you use a net type variable can never be sequential, it will always be combinational, right. Okay. So, this is what I mentioned, the object which you are assigning must remember the last value assigned. This is not continuously driven. So, you must have rich type variables in the left hand side, but on the right hand side or in the event expression you have any statements. Such one by one. If the number of statement is 1, then the begin end keyword is not required. You can simply write the statement, right. Now if else, you see these constructs are very similar to the one which are available in high level languages like C. So if it's true, then, and here as I said that each sequential statement can be sequentially one by one. It first compares with expression 1, then expression 2, expression 3, can be either a single statement on its own, expression 3 up to expression n, and whichever it is matching, the same expression, the way you are comparing, it can match with more than one condition. There can be some don't care values also. So the first one that matches will be the one that will be taken. Like there are two variations of case you can have in Verilog. One is called case Z, other is called case X. In case Z statement, here the high impedance or the Z values in the inputs and the expressions are treated as don't cares. But in case X, not only Z, also this X, they are treated as don't cares. Then next state is 0, you do this. If the second bit is 1, you do this. But if none of this matches, that means none of the bits are 1, then default something you can say, here I am saying next state 0. You see, if your state has a value, let us say 1 0 x x, this will match with the first condition which is 1 x x x, because 0 and x matches, x is don't care and 0 is one possible value of the don't care. Okay? But if you give only case, then these will not match. But if you give case X, then only the first bit is in the state is 1 or not, other 3 can be anything. Okay? Need not be x x x, need be 0 1 x, 0 1 z, anything. Okay? So this is how you can give. So there are several other kind of this kind of constructs also. So we have only seen a few: begin end, if then else, case. So in our, this is what I am saying. So in the last lecture we were discussing some of the procedural assignment statements or the procedural sequential statements in Verilog. So we talked about statements like the begin end block, the if and if else, nested if else, and the multi-way branching using case. Okay? So we continue with our discussion today on procedural assignments. And the first construct that we talk about today is the so-called while loop. Well, this while statement is available in standard. So the general syntax is true means within big, that's why understate statement part of we are using a while loop. It is, this is just for the sake of demonstration and illustration. Going enters the begin block, to here set to 0, comes into the while loop, the my count value will be 0, so it is definitely less than my from 5. In the expression 1 and expression 3, they are actually assignment statements. This expression 1 basically specifies an initial condition or an initialization. Some variables get initialized here, and expression 3 specifies an assignment where some control variable that controls how many times the loop will go on, which checks or it specifies a termination condition. So as long as there be a single, this is a vector of bits of type reg. So it is a vector of size 100 where the index values range from 1 to 100. In the first initial block, we are just doing exactly what we did earlier using the while. So this will be the initial. Then you check will be a loop to its values increase I by 1. Recall loop will specify a condition. So we do not say directly that how many times the loop should go on. So in the while loop, we specify a condition, and as long as that condition is true, I continue executing the loop. Similarly for the for, there is a logical expression we have specified in expression 2, you recall. There we specify a condition again, where as long as that we do not so number that for it here even because a fixed clock as of type reg. Well, I am repeating, you will have to define 0, it will actually 100. This kind of word, right? Next is the forever loop, as I said. This is a version of a loop where you execute the sequential statement infinite number of times, forever. In the forever construct, you do not use any expression or any count value how many times to loop. So you will be continuing with this loop forever. Now with respect to the test bench, if some block executes, so you can say to be that delay blocks, you have to do something. It is intent use example that uses a clock signal indefinitely. So inside the timing delay, here we are. So this event expression can be how we'll see. So it can be some unit nanosecond specified as a pending hash indefinitely because it's a forever loop. But now the time is advancing, okay? 5, 10, 15, 20 it is advancing. So you are not holding up any other statements in the other initial or always blocks. Okay, fine. So the other constructs that are available in Verilog, one of course you have used this time specifier hash followed by some time value. So the meaning of this statement is, so a block that has this kind of timing delay specified at the beginning of it, the block will be suspended for this much amount of time before it gets executed. And the time unit can be specified as I mentioned earlier using the, okay, fine. So the other important construct which I have already seen through some examples, where particularly in the always block you use this is at the rate within bracket some event expression. Here what we are doing, here we are making a block suspend its execution until this event expression triggering, which you can in the event whatever is in the procedural block inside. We mentioned that in this always block also connect to this notation, so change then do this, or you can specify either a positive or negative edge of a signal. This is particularly used for sequential circuit, synchronous. Actually a pause edge is defined as any transition where a signal changes from either hierarchy where x, then you have xz, then you have 0. So any transition, the hierarchy 0 is considered to be lowest. Where we talk about a positive edge, well, a pause edge does not necessarily mean a transition from 0 to 1. So you define a pause edge to 0, pause edge of some variable, let's say x. So whenever the value of a variable x changes from a value which is from 0 to 1 or 0, so let's take some examples of this event true, and the block will be executed. Now in place of or, you can also, so whenever either the positive edge of clock comes or the negative edge of reset comes, you execute the block. Okay, the event you can define a composite event or edge CL either more than one changes, then this condition is considered to be true and the block will be executed. Now in place of or, you can also write a comma, the meaning is the same. So you can either write, I am referring to a clock here. So whenever there is a positive negative edge of reset, and in place of or you can also put comma. Here I am putting a star. You see here 100 variables. Now if I write a star, star means any. If any of the variable changes, execute the block. So in some designs, in some modules, writing a star becomes more convenient, because first thing is that you will not have to write so many variable names, and secondly you may have forgotten to list one of the variables. So you see that your simulation is not coming correctly, maybe you have missed one of the variables, D was not there, but if you write star, then there is no problem. So you know that you have included. So here I am showing the module description of a D type flip-flop with synchronous set and reset. So when I say a flip-flop has synchronous set and reset, it means whenever the clock, the active clock edge comes, setting and reset of the flip-flop takes place. Everything, setting means setting the flip-flop to 1, resetting means or reset. I have, suppose my, so I find it high here, and set is or changes take place at the active edge of the clock, right? Setting and resetting similarly. So let's see the module. We have Q bar, and this Q we are generally initialize always at the clock. Now this means and there is an enable. Good. Clock. There is no clock, okay? So in this always block you are saying D in or enable. So over the last couple of lectures we had seen the various kinds of assignments, data flow and the procedural kinds of assignments. That vector with a variable index, update my value of f. What I do, if s is true, that means s is 1, then this in 1 will go to f, otherwise if s is 0, in 0 will go to f. Now see, whenever you describe something using this OR notation like this, normally we are expressing or trying to express a combinational circuit behavior. But of course there can be exceptions we shall be seeing later, that even if we specify the event expression by naming variables using OR, there are cases where a sequential circuit might be synthesized, but we will try to explain when it happens, okay? But in the example I have given here, it is a simple case of a combinational circuit that will be generated. So here a simple 2-to-1 multiplexer will be generated, okay, where this in 0 and in 1 will be the inputs, this S will be the select line because you are checking on S, and F will be the output. This OR keywords combines the variables to form the event expression, okay. Now I have a slightly modified version of the same program, where in the earlier one we gave OR, okay. So instead of OR we can give commas, same thing. This is just by commas. Now this notation is supported in the recent versions of Verilog, so you can use this. Fine. So as the third variation, so instead of listing the variables I mentioned, we can put a star. What does the star mean? So whenever any of the input variable changes, now here my input variables are in1, in0 and s. So whenever any of them changes, this always block gets actions are equivalent. This because it will make your code shorter. This is an explicit synchronous D type negative edge triggered flip flop where you are using a clock with a negage. Doing negage means whenever this signal is having a negative counts in binary. Suppose it is a 4-bit counter, it is active, immediately I can initialize the counter to 0. So let's see how the description will be. So here clock and reset are the inputs, and count, here is the example of 4-bit counter. So, the count value is of 4 bits, which is output, which is also reg again because the clock. Okay, here this is a little surprising example. See, first thing is that here we have mentioned in the comment that another sequential logic example, but you look at the description, does it look like a sequential circuit or sequential circuit description? Let us look at it in some detail. This is the module, this is the name of the module, just forget the name for the time being. There are two parameters, current state and flag. Current state is a 2-bit vector 0 1, flag is also a 2-bit quantity which is output, also reg because flag is appearing on the left hand side. Now, let us look at our procedural block. Well, always whenever the current state changes, you do this. So, what is my logic? My logic is case, there is a case statement. So, I check the current state. So, if the current state is either 0 or 1, so in case if there are multiple cases which can result in the same expression, you can separate them by commas like in the example shows. If it is 0 or 1, you set flag to 2. If it is 3, you set flag to 0. Now the question is, why am I calling it a sequential logic? So, it is clearly like a combination logic now, just you try to construct a truth table kind of a thing. Suppose I am listing my current state and the expected value of flag which I am setting. So, according to my description, if my current state is 0, I set flag to 2. If my current state is 1, I set flag to 2 again. If my current state is 3, I set flag to 0. So, it is just like a combination circuit, but there is a catch here. Here we have not specified what will happen if the current state is 2. So, we have not specified the value of the flag. So, what is the meaning? Now, the Verilog simulator or the synthesizer will assume the meaning as follows: if some of the input descriptions are missing in the case statement, like here the value 2 was missing, the interpretation will be if current state is 2, then flag will not change. Because we have not specified the value of flag, the interpretation will be the value of flag will remain what it was in the previous state, which implies that flag will map to a storage element, means latch. So, you will have to store it just for this purpose. Okay. So, whenever there is an incomplete specification, in order to satisfy the interpretation that the Verilog simulator or the synthesizer assumes, that if it is one of those unspecified condition, the output value will not change. To implement that, the output value has to be stored somewhere in a latch, which implies this becomes a sequential circuit, not a combination circuit anymore. Okay. So, for this example, the variable flag is not assigned a value in all the cases of all the conditions of the case statement. 0, 1, 3 we have specified, but for 2 we have not specified. Because flag is a 2-bit register, so a 2-bit latch will be generated for the flag. This is how it will work, right? Now, you see, I mean, as a designer, I know that if I specify a circuit like this by not specifying all the conditions, case conditions, then the synthesizer will be generating a latch. Well, although I do not want this to be a sequential circuit. So, how can I modify it? I can make a small change in my description, like I can just add one line here, remaining part is identical, just one line here before the case. Before the case, I add one line. Now, there are two statements, that is why I have given a begin end, flag 0. So, now what is the difference? Now, the synthesizer or the simulator, if it does a data flow analysis, it will find that, well, for 0 and 1 flag is 2, for 3 flag is 0, but for the condition 2 also flag will be 0 because we have already initialized flag to 0 and have entered. So, if I do not specify, flag will remain at 0. So, now if you look at this truth table we have constructed earlier, now for this case, instead of a question mark here, this value will also become 0. So, this will be a pure combinational circuit and there will be no latches that will be generated. So, as a designer, it will be your responsibility to write the specifications in such a way that latch is not generated unnecessarily unless you explicitly want it to be generated. Okay, fine. Okay. So, here as I said, by doing this, the variable flag is getting defined for all possible values of current state, which implies that a pure combinational circuit will be generated by the synthesis tool and the latch, as in the previous example, will be avoided. Okay. So to summarize our observation, whatever we saw, that when you use a case statement in a Verilog description and case statement is incompletely specified, that means all conditions are not given, then the synthesis tool will generate a latch to hold the output values, because whenever one of those unspecified values are coming, so the synthesis tool will try to keep the output in the previous state, and for that it needs it to store it in a latch. Now, as I said, it will be up to the designer finally to code it in such a way that latch can be avoided, because if you specify your design in such a way that it is incompletely specified, the synthesis tool will assume that as a designer you are wanting to create a latch, and a latch will be created. Well, let's take a very simple example to basically consolidate this observation once more. Let's take a very simple example. Suppose we are, see the input, you can specify same line option goes like, so if A is 1, you assign B and C to F. Now you see here I have not used a case statement, but there is a conditional if else kind of thing. So the situation is very similar. Here also we are not specifying the value to be assigned to F for all possible values of A. We say that if A equal to 1, interpretation will be F. So if you latch, for this will go to the D input, and the input A will go to the enable input, and the output Q will be your F. You see, this exactly models this behavior what you have given. If A equal to 1, so whenever A equal to 1, this enable will be active, and BC will be stored in the latch, and that will be available on F. But if A equal to 0, which means you are not enabling the latch, so your previous value stored in the latch will remain in F. Okay, this is what you wanted. Now let us look at a slightly modified version of the description. Say, then F will get the value of B and C, and for A equal to 0, I have already initialized F to some value. So this will be the value when F is 0. So I have defined now F for both conditions. Sorry, for A equal to 0. For A equal to 0, this will be condition. For A equal to 1, this will be the condition. So now I have specified the value of the output F for all values of A. So now if you give this description to the synthesis tool will be possibly generating a circuit like this. To generate BC, there will be an AND gate, then it will be synthesizing a multiplexer, a 2 to 1 multiplexer, where the other input of the multiplexer will be C, this will be your input 0, input 1, and your select line will be A. The output will be F. So see what is happening here? You are saying when A equal to 0, C should go to F. So if A equal to 0, C will be selected, and if A is 1, this will be selected, BC will be selected, BC will go to F. So this is a purely combination circuit, you see. So this is something which is up to the designer. So you will have to design it in a proper way so that the synthesis tool should not get confused and generate a latch where what you actually wanted is a combination circuit, right? So it is greatly up to the designer to specify how you are wanting to guide the synthesis tool. So you should not mislead the synthesis tool in believing more examples. So here we have a very simple 4-bit arithmetic logic unit where the parameters are F, A, B and op. But op specifies, these are 2-bit, it specifies one of 4 operations, and A, B are 8-bit inputs. This F is also an 8-bit output which is of type reg, because F is on the left hand side. Well, using parameter command you can specify some constants. I gave some example earlier. Like here suppose we are supporting 4 operations: addition, subtraction, multiplication and division. Now to make our program more readable, we have specified them as add, sub, mul and div, where add means this op is 0 0, sub means 0 1, mul is 1 0, div is 1 1. And here we have an always block where you are saying whenever it is star, that means any of the input changes depending on the value of op. But instead of writing 0 0 0 1 1 0 1 1, I straight away am writing add, sub, mul, div. So it becomes much easier to understand the code. So the operation is given directly. Okay? So this is a very simple way to specify an ALU in a behavioral fashion, right? Fine. This is another example of a priority encoder. This priority encoder has 8 inputs and it has 3 outputs. So what is a priority encoder? So a priority encoder, the example that I have said, there are 8 inputs and there are 3 outputs, and inputs are given some index values 0 1 2 3 4 5 6 7. Now I am assuming that the priority increases in this fashion. My input 0 has a higher priority than input 7. Now the idea is that suppose I set the input number 2 to 1 and the others are all zeros, then the binary equivalent of 2, which is 0 and 0, should appear in the output. Now let us take an example where any 2 of them are 1. Let us say this input 1 is also 1, input 4 is also 1, the others are zeros. So if more than one of the inputs are at 1, then according to the priority you choose the one which is highest priority, that is 1. So binary equivalent of 1 0 0 1, this should be in the output. So this is how a priority encoder works. So let us see the description. So the input is an 8-bit vector, this is the output, code is a 3-bit vector of reg because it appears on the left hand side. So again in the always block, whenever there is a change in, there is a begin with a nested if. If in 0 means in 0 is true, which means in 0 is equal to 1. If in 0, code equal to 0 0 0. Else if in 1, code is 0 0 1, simple. If in 7, 1 1 1, and if none of them I have checked the bits, that will define the priority. So if both your in 1 and in 4 are active, but I will get a match in 1 first, so code will become 0 0 1. So, as I said, the input bits are checked. Input BCD to 7 segment decoder. Now, BCD, you know, BCD is a way of encoding decimal numbers. Decimal digits are 0 to 9. They can be coded in 4 bits, 0000 up to 1001, that is 9. Okay. Now, 7 segment display looks like this, where there are, means either LEDs or LCDs, whatever. There are 7 glow sum of 0 up to what size -1. So, for 16 it will be 15 to 0. Right? The input is like I said, this specifying this is then greater than 1 will be assigned this equality a minus b. Suppose 0 1 1 means logical not, ALU range equal to bit by not, and if it is any one of the others, so in case I can mention default, then I initialize ALU range to 0. So, this example illustrates the combination of assign and case in always block and so on. This also generates a combination circuit. So, with this we come to the end of this lecture. In this lecture we have looked at a number of different examples, various ways of using the procedural style of coding, the always block, the different ways of using always block and so on. And we shall be continuing these discussions later and look at more complex and more elaborate structures using which we can model particularly the sequential circuits and finite state machines. Till then, we will have to wait for the next lectures. Thank you. So, we have been talking about various kinds of assignment statements in Verilog. So, recall we talked about the continuous assignment statement using assign. Then we talked about the procedural assignment statement. So, looked at several examples where inside an always block or inside an initial block we can use various kinds of assignments to variables. These are called procedural kind of assignments. Now, broadly speaking, these procedural kind of assignments come in two different flavors. So, in this lecture we shall be starting our discussion to clearly distinguish and try to find out when and under what conditions should we use which of these two options or alternatives. So, the topic of our lecture today is blocking and non-blocking assignments. These are the two types that I was talking about. Fine. So, these assignment statements fall under the broad category of procedural assignments. So, what do you mean by procedural assignment? Procedural assignment is an assignment, an expression which assigns some value to a variable which lies or figures inside a procedural block, is an assignment alternatives. So, the topic of our lecture today is blocking and non-blocking assignments. These are the two types that I was talking about. Fine. So, these assignment statements fall under the broad category of procedural assignments. So, what do you mean by procedural assignment? Procedural assignment is an assignment, an expression which assigns some value to a variable which lies or figures inside a procedural block. In Verilog, a procedural block can be either initial or always. Okay? Procedural block. In Verilog, a procedural block can be either initial or always. Okay? So, these kind of procedural assignment statements can be used to update variables only of these types: reg, integer, real, or if you have a time variable which keeps track of time. You see, you cannot have a net type variable on the left hand side of a procedural assignment. This is the restriction. So, if you are using some variable to assign a value inside a procedural block, they have to be one of these data types. Now you see there is also a very clear difference from the continuous assignment type. See, in continuous assignment which we had seen earlier using assign, let us say we write assign a equal to b plus c. Here whenever the value of b plus c changes, the value of a will be immediately changing. It will be directly driving this net type variable on the left, and this net type variable on the left of this assign statement do not have any facility or capability of storing this value. That is why we call this as continuously driven. As b and c changes, a will be continuously changing, right? But in contrast, for a procedural assignment, there is an important difference to be remembered. The value that we assign to a variable, this remains unchanged until you assign some other value to that same variable again. Okay? So there is some notion of storage or memory associated with the variables that you use here. So once you assign some value to a variable, the value will remain unchanged until you again assign it to some other value. So this is the difference from assign which I just now talked about. So broadly speaking, these assignment statements inside procedural blocks can be blocking or non-blocking, and they are denoted by the assignment operator. Blocking is denoted by equal to, non-blocking is denoted by the arrow symbol less than equal to, this symbol. This means arrow. Okay, fine. So the rules for a procedural assignment statements are as follows. So I already talked about that the variable on the left hand side should be one of range, integer, real or time. This is of course a constraint. Not only this, on the left hand side we can also have a bit select of one of the variables of this type, like you can write sum 15 equal to something, right? This is one particular bit of a data of this type, or if this by a variable c. These and these outside assignment, and let us try to understand what it really means. Now the general syntax is, on the left hand side you have the variable name of the types, one of the types I mentioned, equal to, well, you can mention some kind of triggering event, like you can mention a delay, or you can also mention an event like at some clock age or something, that also you can mention. Variable name equal to some expression. So for the time being, let us ignore this. Variable name equal to some expression, this is the general syntax, and this equal to symbol is used to indicate blocking assignment. So what is the meaning of blocking assignment? You see, so if inside a block there are several statements, the statements will be executed one by one in the order they are specified. Like suppose inside a procedural block begin end I have 4 statements. The statement will be executed one after the other in sequence. Suppose the first statement is a equal to b plus c. So some value will be assigned to a. Second statement is, let us say, d equal to a plus 5. So that value of a which was assigned, that value of a will be used, okay, in the next expression. So in that way, one by one sequentially action which is executing or an assignment, right, in one of the blocks. Now this blocking assignment style can be used to model sequential circuits also, but it is recommended that we use this assignment style to model combination logic. We shall see a lot of examples later and try to find out why this is so. This is what I mentioned. So using blocking assignment you can also generate sequential circuit elements. So means we had seen some examples earlier, you recall those examples where you had a multi-way branching using case, where if all the values of the case variable were not specified. Suppose I am doing a case on a variable a which can take on the value 0, 1, 2 and 3, but I specify what will happen if the values are 0, 1 and 3, but for 2 I am not specifying. So if the value is 2, what will happen? So all the variables which appear on the left hand side, they should not change, which means they should remember or memorize their value. So the synthesis tool, what it will do, it will be generating a latch, a storage, memorize this which appear on the left hand side. So I am not specifying. So if the value is 2, what will happen? So all the variables which appear on the left hand side, they should not change, which means they should remember or memorize their value. So the synthesis tool, what it will do, it will be generating a latch, a storage element for such variables. But if in the case statement you mention all the conditions without any ambiguity, then it will generate a pure combination circuit. So earlier we took some examples to explain these things. Okay, fine. So an example of blocking assignment is shown here. This is not the complete Verilog module, just a segment of the module. Let us say ABC are 3 variables of type integer. So inside the initial block I have this begin end. So see the statements A10, B20, C15. These are the 3 statements, one by one they will get executed. So initially this ABC will be getting the values 10, then B20, then C15. It will be 35. So the new value of A will become 35. The next statement is B40, and the last statement is C equal to A minus B. So the latest value of A and the latest value of B, they are subtracted and the result will be minus 5. So this is the interpretation of the blocking assignment. Statements fine illustrated are shown. Here we are defining 3 variables x, y, z and 2 vectors of size 32 AB. This is not a meaningful code, just an illustration. So you see at the beginning we give some assignments, tables, assignments 31 bit AB, AB, of A will be changed to 1 at time 5. Then I give another delay 10. So, I define a segment of B, these 3 bits 29, 30 and 31, they will be assigned a value which will be the concatenation of x, y and z, and this will happen after delay of 15, which means at time 15. And lastly, sum we are incrementing by 5. So, again because there is no delay here, this will also happen at time 15. Okay. This is just an example showing how the times are kept track of in blocking assignments. The results through simulation, because there are a few things to understand here. This is the example that we take, 4 variables defined A, B, C, D. This is always block, always at the rate star means any variable changes, and inside this block we are saying repeat this block 4 times. So, I am saying this begin end block has to be executed 4 times, and each of them will be having a delay of 5 time, then is. So, we start by initializing A to 30, B 20, C 50, we call finish. Variables change like this. So, the point to note is only the next step. You can execute concurrently. This is implies a non-blocking assignment statement, then club that block. So, here we will explain currently. This is just a test bench I am writing, there is no clock. There are 3 variables A, B and C, and in the second initialized block I am using non-blocking state inside a procedural. They will be evaluating together using the current values of A, B and C, and after the delay which is specified, they will all be concurrently assigned to the variables on the left. Okay. So, in this example, let us say A is 10, B is 20, C is 15. So, on the right hand side, B plus C, A plus 5 and A minus B will be evaluated first. What is B plus C? So, they will be assigned the final statement. So, when you use behavior of inside expressions are evaluated together based on the time 5. Whenever there is a positive edge of a clock, you compute the edge of a clock. You see signal. The right hand side is modeling synchronous. You want to swap the value of 2 variables A and B. Swapping means if A is 10 and B is 20, so we want to make A 20 and B 10, interchange their values. Let us look at various styles of doing it and using non-blocking assignment with 2 always blocks. Both are activated at the positive of clock, there is no delay. So, you see, because these are concurrent blocks, A equal to B and B equal to A, they are actually executing concurrently. But you see, when you are simulating this, depending on the simulator will be either doing this assignment first and then this, or the reverse. So, if A equal to B is done first, then B that was there in A, execute A, instead there is no problem, because these assignments will take place only when positive edge of clock comes, and they will take place together. So, the to A and B, okay, it can be either this, then the variables will be correctly swapped, because the right hand side variables skip clock edge. At A equal to B, B equal to A, what will happen? Inside the same block, just try to see what will happen here. First, this statement will be executing, B will be copied to A, and then this will, because this is the first statement to execute, the value B if it is 20, the previous value. Swap, you can do it like this by using 2 additional temporary variables, then using one example. So, and in a for while loop, we are generating the clock signals. So, into D plus, and these are combination specifying that you should not mix blocking and non-blocking assignments together in the same block. Well, it is not that it is not allowed. I shall show you some examples later where you will show that what will happen if you mix them, but it can make the things complicated for you. Simulator or the synthesizer may allow, but this is certainly not a good design practice. You should avoid this. You use either blocking or non-blocking inside a particular procedural block. Only for the design to work, clearly the differences between the two and what will happen if various types of combinations you use, it will be difficult for you to understand the interpretation of this. So, in this lecture, we shall be looking at some of the examples where we will be using both blocking and the non-blocking styles, and we shall see some of the features and some of the issues that might happen or that might arise. So, this is our part 2 of this lecture. Fine. So, as I said, so we shall be looking at some errors which are best avoided. These are avoid using both. Now, just to tell you, an 8-line 2-1 multiplexer, what is the schematic we are looking at? So, we are looking at a 8 to 1 multiplexer whose output is out. There are 3 select lines which we call as SEL, and there are 8 input lines. Okay. The input lines are called in. So, depending on the select line, one of the input will be selected. Now, earlier we had seen that we can very easily model a multiplexer using an assign statement, like we can write assign out equal to in cell. So, if we use a vector on the right hand side with a variable as the index, this will generate a multiplexer. This is what we mentioned. But here we are going a little bit into the behavior of it, but instead of using assign statement, we are trying to use a procedural block to model a multiplexer. So how we do it? We are using an always block. So let's see. Here the parameters are in, cell, and out. In is the input. There are 8 lines. Select line, there are 3 bits, and output. See, this output we are declaring as reg because inside this always block we are assigning some value to this out. So I mentioned inside the procedural block the left hand side has to be either reg or an integer or a real or a time variable. Okay, so here we have defined it as type reg. Okay. Now here we are saying that always at the rate star, whenever some values change, input values change either in or cell, you do this. It's a simple case statement on cell. Here we are just enumerating all 8 binary combinations 0001, then in 1 will be assigned to out and so on. If it is 111, in 7 will be assigned to out. Now you see at the end we have given a default case which says that we are initializing some undefined value to out. Now you may ask that, well, we have already defined all possible 8 combinations here in the case, so why do you need to specify default? Oh, okay, so you remember that in Verilog we mentioned when we talked about variables and their values that Verilog is actually a 4-valued logic modeling system. So every variable can assume a value not only 0 and 1 but also x and z. Due to some problem in the test bench or the circuit which is driving, maybe you have not initialized some variable in a proper way. The select line may be coming here as an x value. So what will happen? So it will not match with any one of 000001 up to 111. So it's a different value x. So for those cases it will go to the default option. So it will get matched to the default, and the output will also be set to undefined x in that case, right? So this is a multiplexer. The next example we take is a synchronous up-down counter. Now let us again look at what kind of circuit we are talking about. Here we are talking about a circuit which is a up-down counter, which can count up or which can also count down. Here the count value, which is the output, this we are calling as count. Now we can initialize the value of the counter. There is another input called d in. There is an input called clear. I can clear the counter to 0. I can load the counter with this input value d in if I want, and of course there is a clock. These are my signal values in this counter. So I can clear it to all zeros, so I can load it with any value I want, and if I apply a clock it will count. And then of course there is another input called mode. Mode will tell whether I am going to count up or count down. If mode equal to 0, it means I want to count down. If mode equal to 1, it means I want to count up, right? This is the circuit which we want to declare all the synchronous. If mode is 1, decrement it by 1, down count. This kind of non-blocking statement, we can model this count in a very convenient way. Well, of course here the statements are not executing concurrently because of the if then else. Exactly one of them will be executing, okay? But there could have been more statements also. Next, let us look at a parameterized design. Here we define with 2 different clocks. The clocks may be of different phases, different frequencies, assigned A or B. Let us say here at the negative edge you are doing T assigned, example which shows some addition and subtraction. I am using 2 edges. So at the first edge I am computing a value T, and at the second edge I am using that value T to compute some other final value F, and this will go on repeating, right? So this is one way or one technique using which we can actually carry out 2 operations within a single clock period. We can do something in the rising edge of the clock, something else in the falling edge of the clock, and one of the values may be fed to the input. We can do something in one technique, go on T, continue F assigned, you are doing B. T assigned A or B. Let us say here at the negative edge you are doing T assigned A B clock. Let us make another declaration. Let us say we define input. Let us say we have 8 bits and we define A, B, C and D, all of them. Let us declare like this. This A, B, C, D all are 8-bit inputs, let us say. And this F is a edge, T is also a edge. T is not required here, of course. C, let us make it T. No, fine, it's fine. This T is not required, so T value F. At the rising edge you are doing some computation, at the falling edge you are doing some computation. Just recall, ring counter is nothing but a shift register. So I am showing a 4-bit ring counter. It is just a shift register comprising of several D flip flops. So, the output of one flip flop is connected to the input of the other. Ring counter means they are connected as a ring, as a chain, and this counter is initialized typically to the state 1 0 0 0, and the clock signal is applied to all the flip flops together. This is the clock. So, if you initialize this shift register with 1 0 0 0, and if you go on applying the clock, so what will happen? Initially it was 1 0 0 0. After one clock it will be rotating right by one place. So, this 1 will be shifted here. So, this 0 will come back, 0 will come here. Next clock this 1 will come here, this 0 will again come back, 0 0 1 0. Next clock 0 0 0 1. Here in this design we are showing you an 8-bit ring counter. So, we have a clock, we have an init signal which will be initializing the ring counter to a single 1 and the all zeros, and the output of the counter which is count. So, clock and init are the inputs and count is the output, which is edge. So, every time when there is a clock edge, pause edge, we are checking that if init is active, init is 1. Well, if init is 1, we are initializing count to this 1 0 0 0. You see here we are using blocking assignment statement, else begin 7 descriptive bit variable, right. So, I have 1 here and there are 7 zeros, 8 is a action of a ring counter. So, these two statements, do they actually do the shifting correctly? Just see, count is an 8-bit variable, right. So, let me just show you. Count is, so I have 1 by 1, will shift left, this 1 will disappear, and then you are saying count 0 equal to count 7 to make the rotator, but this count 7 has already become 0. So, even if you store this 0 here, this value will still remain 0, this 1 will not come back. Okay. So, means after a rotate operation, after this begin and block, the count value will become all 0, and after that it will remain all 0. Okay. So, this is not a correct description of a ring counter. So, as I said, this solution is wrong. This count 7 rectify. See here what will happen. Here we are doing the same thing, but we are using a non-blocking assignment. Let us see what will happen. So, now our statement shift left by 1, count 7. Now, again let us look at the count. This is an 8 bits, 2, 3, 4. Non-blocking assignments less than 0, count 7 is 1. Now, you are assigning them together. So, when you are just assigning them, this count 7 1, this is also bit getting. Now, in fact, even without using this non-blocking, we can have a correct version like this. Suppose I write my blocking assignment like this. I write count equal to count 6 to 0 and count 7 concatenated. What does this mean? Count 6 to 0 means, you see, this rotate left and right. Okay, fine. So, you will be able to find out that. Now, in the next lecture, we shall be continuing with some other aspects of blocking and non-blocking assignments. Till then, you can. So, we continue with a discussion on the blocking and non-blocking assignments. So, in this lecture, we shall be looking at some more differences in the way they behave and the way the synthesis or the simulation tool will interpret or handle the description that you have given or provided in either blocking or non-blocking kind of assignments. Okay. So, we shall be illustrating these points through a number of examples. That will be the best way to just explain. So, actually through the examples we shall be showing you some modeling styles, some modeling styles using both blocking assignment and also using non-blocking assignments. And there we will try to understand by looking at the semantics or the meaning of those statements, how the simulator or the synthesis tool might be influenced to capture the behavior of your model in a particular way, that whether it is actually capturing the behavior in the way you are intending or it is doing something else. Okay. So, as these are something which is extremely important from the point of view of the designer, because you have to understand these blocking and non-blocking statements very clearly, because if you do not model the behavior of your circuit or system that you want to in the proper way, then even a very small error in the model which might easily be overlooked, that might result in a drastically different output or a drastically different circuit depending on whether you are simulating or synthesizing. Okay. So, we shall be trying to see some examples. Now, there is another thing I mentioned repeatedly, that when you are studying some codes, when you are learning some constructs of a language, so it is always recommended that you actually run the code. Say for Verilog, you simulate it and see how the outputs are coming, change the code and see what are the changes that are happening. Okay. Okay. So, the first example that I take is a simple timed assignment using blocking and non-blocking, a very simple segment of code. So, inside a block, begin and block, this can be inside either always or initial, whatever, some procedural block. I write blocking assignment after delay of 5 b, c equal to after delay of 5 a, and here similar but non-blocking. So, let us try to understand what will happen here. Blocking statements will be executing one after the other. First statement will say that after a time delay of 5, b will be assigned to a. Second statement says after this is finished, only then it will come to the second statement. So, after another time delay of 5, that value of a will be copied to c. So, the value of b which was there, it first goes to a and then it goes to c. So, the value of b will be finally assigned to c after a delay of 10 time units, right. This will happen here. Now, if you use a non-blocking assignment statement, what will this mean? This will mean here the time delay does not mean that you first finish this after time 5, then again after time 5 do this. No, it will mean that you evaluate the right hand sides. See, a is scheduled to get the value of b 5 time units into the future. Right hand sides are evaluated together, and when you say #5 and #5, it does not mean like this, that first this 5 and then this 5, this is actually 10, not this. Both of these are waiting for time 5 and they are assigning, they are executing concurrently, right. So, here b will be assigned after time 5 to a will be also assigned after time 5 to c. So, you see in the first case here the value of b was assigned to c, but here finally the value of a will get assigned to c, right. So, the final value of c will be different for these two cases. This is a very simple example, but you will have to understand the difference very clearly, what this #5 here and what this #5 here means. So, when you are using a blocking assignment, I am repeating, if you are using those delays, because in a blocking assignment statement, the statements will be executed one after the other, the delays will get accumulated. If you give 5, 5, 5, it will be 5, 10, 15, 20, that way the delays will get accumulated. But in a non-blocking case, it is not so. There the delay means you evaluate all the right hand sides together, and after how much time you will be assigning it to the left hand side. If you give all then #5, #5, #5, means after a delay of 5, all of them will be assigned together. It is not that the delays will be adding up, not like that. Okay. So, because of that, for these two cases, the final value of c was coming to be different. Let us take another example. This is a procedural block with a clock, always POSH clock. Here I am using a blocking assignment. So, what does this block mean? This block means that whenever there is a positive edge of the clock, you activate or start executing this. What is this saying? That you first assign a to q1, in turn comes execute. So, it will post look equal to a. What does this mean? You see, you can imagine there will be two flip flops. q1 will be the output of one of the flip flop, q2 will be the output of the other flip flop. First one, you are saying that q1 will be going to q2, which means this q1 has to be connected to the input of this, q1 will have to go to q2. Second one, you are saying some other value, because after this is completed only then you will come here, a will go to q1. So, some other value a will go to q1. So, the old value of q1 will go to q2, this a will be going to Q1. You see, what we are trying to say is nothing but a shift register. If you write it in the other way around by interchanging the order, what you are saying is just a 2-bit shift register. Q1 will be shifting to Q2 and this A will be shifting into Q1. Okay? So the same thing will happen for the non-blocking case also. Non-blocking means the same thing. Q1 will go to Q2, A will go to Q1. The order is not important because in whatever we just order you mentioned. So the hardware that will be synthesized will be a 2-bit shift register. Q1 will go to Q2, A will go to Q1. So here also A goes to Q1, A goes to Q1, Q1 goes to Q2, Q1 goes to Q2. So the previous values of A and Q1, previous value of A, previous value of Q1, they will be assigned to Q1 and Q2. This will be assigned to Q1, previous value of Q1 will be assigned to Q2. So both of these descriptions model a shift register. So one thing you understand, for a blocking case, it is very peculiar. So if you write the two statements in a particular order, then it will generate two flip-flops in parallel. But if you simply interchange them, it will become a shift register. So peculiar. So if you write the two statements in a particular order, then it will generate two flip-flops in parallel. But if you simply interchange them, it will become a shift register. So this you will be able to understand only if you know what is the meaning of the blocking assignments. If there are some statements, what you will be able to understand. So I simply interchange the order. I just write it like this. And below I write an description, same description using non-blocking assignment. Here let us try to understand what will happen. Here we have written Q2 equal to Q1 and Q1 equal to A. What does this mean? You see, you can imagine there will be two flip-flops. Q1 will be the output of one of the flip-flop, Q2 will be 2, which means this Q1 has to be connected to the input of this. Q1 will have to go to Q2. Second, so some other this A will be going to Q1. You see, what we are trying to say is nothing but a shift register. If you write it in the other way around by interchanging the order, what you are saying is just a 2-bit shift register. Q1 will be shifting to Q2 and this A will be shifting into Q1. Okay? So the same thing will happen for the non-blocking case also. Non-blocking means the same thing. Q1 will go to Q2, A will go to Q1. The order is not important because in whatever we just order you mentioned. So the hardware that will be synthesized will be a 2-bit shift register. Q1 will go to Q2, A will go to Q1. So here also A goes to Q1, A goes to previous value of Q1, they will be assigned to Q1, model a shift register. So one thing you understand, for a blocking case, it is very peculiar. So if you write the two statements in a particular order, then it will generate two flip-flops in parallel. But if you simply interchange them, it will become a shift register. So this you will be able to understand only if you know what is the meaning of the blocking assignments. If there are some statements, what exactly is the meaning and how. So let us continue. Both on positive edge. Here you are saying at the positive edge Q1 will go to Q2, also the positive edge A will go to Q1. Just if you move back in the previous slide, you see here we used a single procedural block, but you are doing the same thing at the positive edge blocks, but both are activating in positive edge and the assignment will take place in a very similar way. So here also, here there are two different always blocks. So in the earlier case we said that the two statements were inside a single always block, which means they are concurrently. Maybe there are blocking assignments, but Q1 equal to A and Q2 equal to Q1, both will be executing together whenever pause edge of the clock comes. So now you see what will happen. Well, Q1 will go to Q2 is fine, but A will be going to Q1. Now in terms of the hardware, just see. So what we are trying to say is this. First statement says A will go to Q1, that means A will go to Q1. Second statement says Q1 will go to Q2. So some Q1 will go to Q2, both at the positive edge. But the value of Q2 will be indeterminate because what will be this Q1 here? Will it be the old value of Q1 or this new value of Q1 which you have just now loaded into Q1 from A? This description is a little ambiguous. If you use blocking statements here, this description is ambiguous and you should avoid this because it executes this. So whatever is the old value of Q1, it will be assigned to Q2. Then A will be assigned to Q1. But if it executes this first, then the new value of A1, the interpretation of the meaning may not be unique depending on the order of the execution, that there is a The crux is that you should try to avoid clock triggered assignment on blocking statement as far as possible. Whenever you want to carry out assignment with clock triggering, better to use non-blocking, then all these problems will not occur. Okay, fine. Let's look at another example which is slightly more complex, a little bigger. Well, here our objective was to design a 4-bit shift register. Suppose this was what we started to design. So, we wanted to design a 4-bit shift register like this. Is 0. This is what I was means actually models a shift register like our A and E here. So, you see small change. We simply going to have one will not matter. The statements can appear in any order. Still, it will be a shift register. So, in this lecture, we shall be looking at some features of blocking and non-blocking assignments which are not recommended to be used, like mixing both blocking and non-blocking statements in the same procedural block. This is the first thing we shall be looking at, and then we shall be talking about a feature in Verilog. There is a statement called generate, with which you can automatically and dynamically generate code in Verilog. So, we shall see these features in this lecture. Let us see. So, the first thing that we will be looking at very briefly, because this is not recommended, I shall not go into the detail. This is mixing blocking and non-blocking assignments within and inside a single procedural block. This I am not going into the detail because this is a very bad design practice. Okay. So, the idea is that the simulation and the synthesis tools that are available, they support using both blocking and non-blocking assignments inside the same always or initial procedural blocks. But again, like the examples that we took in the last lecture, there we looked at only blocking assignment. Still then we saw that there are a lot of confusions. The order of the statements, so this I am not going into the detail because this is a very bad design practice of procedural block. This I am not going into the detail because this is a very bad design practice. Okay. So, the idea is that the simulation and the synthesis tools that are available, they support using both blocking and non-blocking assignments inside the same always or initial. Procedural blocks. But again, like the examples that we took in the last lecture, there we looked at only blocking assignment. Still then we saw that there are a lot of confusions. The order of the statements that you put, that becomes very important, which is not so for non-blocking. But if you mix them up, the problem becomes even more complicated, right. So, if you mix them up, the interpretation exactly what the circuit is supposed to behave like is not very straightforward, and hence it is not recommended. Okay. So, we shall be looking at two very simple examples, and I am repeating, such mixings should be avoided in an actual design. Okay. So, let us take a simple example like this. In the first example, we are using only blocking type assignments. always at start, x equal to 10, x equal to 20, y equal to x, and then a delay of 10 here, and this is repeating, okay. And here the last one we are using a non-blocking assignment. You see, for both these cases, what is the meaning? Blocking assignment means you first execute the first statement, 10 is assigned to x, then execute the second statement, 20 is assigned to x, then execute the third statement, 20 is assigned to y, okay. So this x will get 20, and finally y will also get 20, both x and y will get 20. Now in the second case, you see the first two are blocking, third one is non-blocking. So the blocking statements, because they are not given any delay, they will be executing at time t equal to 0. So at time t equal to 0, x will be getting 10 and then x will be getting 20 in this order, but both will happen at time t equal to 0 only. So the final value of x will be 20, and this non-blocking assignment will take or evaluate the right hand side at time t equal to 0, and at time t equal to 0 this x has already become 20 because the time has not advanced, time is still t equal to 0 inside this loop. So that latest value of 20 will be taken and the same 20 will be assigned. You see, this is actually quite confusing, you should not mix it like this, but if you use this, you will see, if you simulate this, you can see that it is getting x equal to 20, y equal to 20, same value you are getting, right. So this is one example, and the other example is that slightly different example, x equal to 10, y equal to x, x equal to 20. And here the middle statement we have changed it to a non-blocking assignment. Here let us see, the first one let us try to interpret. These are all blocking assignments. First x gets 10, then 10 gets assigned to y, then 20 gets assigned to x. So the final value of x will be 20 and the value of y will be 10. But here what will happen? Here you see the order is important. The blocking assignment will interpret is that, well, once everything before me has finished, only then I will start. So x will get the value 10, then it will wait, okay, because there is something before it. So this 10 will be assigned to y, then this will come, 20 will be assigned to x. So this is again very confusing. But the simulator interprets it like this. If you simulate it using Verilog, you will see that if you simulate both the designs, you will be getting later. You will see that you can have multiple always blocks. So in one of the always blocks, you can use only non-blocking assignments. In some other always block, you can use only blocking assignments. Such things are sometimes required in design. We shall see later when you talk about designing sequential circuits, designing finite state machines, and so on. Okay, fine. So we shall not be discussing any more on this. Now we come to a very useful feature that is available in Verilog, which is called generate. Let me try to give you a brief motivation. What is this all about? Well, we took an example of a ripple carry adder earlier, if you recall. So a ripple carry adder is constructed by simply connecting a number of full adders in cascade. The carry out of a full adder is connected to the carry in of a full adder, the carry out of the second is connected to the carry in of the third, and so on. So if I want to design a 4-bit ripple carry adder, I will be connecting 4 such full adders. Now if I want an 8-bit carry look ahead adder, I will be connecting 8 such. Suppose I tell you I want you to design a 32-bit ripple carry adder. Then means using the way which you have learned so far, you will have to instantiate the full adder 32 times, isn't it? 32 copies of full adders are required, and they will be connected like that. You will have to mention in the carry values also. Carry out will be carry in of the next one. So 32 lines of code you have to write. Now you may think, so isn't it quite logical that the language should provide a feature of some kind of iteration or loop? So I can say that I want 32 copies of full adder. I specified only once, and 32 copies will be generated. So this generate block does exactly that. It dynamically creates multiple copies of your design or specification, whatever you have written in Verilog, to suit a particular design. So we shall be looking at some examples. Generate blocks. So there is a statement called generate. Generate is a keyword. Generate statements, as I mentioned, this allows the simulator or the synthesizer to generate Verilog code dynamically before they can be used. This is a very convenient feature to create so-called parameterized module descriptions. So I mentioned these parameters earlier. You can define a constant. So you can define an n-bit ripple carry adder for arbitrary value of n. this is an example of a parameterized design. N is a parameter, you change the value of n, you get a 4-bit adder, 8-bit adder, 16-bit adder, whatever you want, just change the value of n. But the Verilog code remains the same, you need not have to change the code. The generate block will automatically do it for you, right. So there are two keywords you require, generate and end generate. So what generate block does is it creates some kind of instantiation of Verilog blocks number of times as you want. Now these Verilog blocks that you can repeat or you can generate, they can consist of modules, user driven primitives, gates, continuous assignments, initial block, always block, anything, almost any kind of blocks you can use for this kind of repetitive generation. And also we shall see through some examples that when you create, say for example, multiple copies of the full adder, so each copy of the full adder will be given some name so that you can refer to the signals in, for example, full adder number 5, the sum of the full adder number 5, you can refer to by a name, that name dot sum, which will mean that will be sum of that particular full adder. We will see how to do it. So the generated instances will have some unique identifier names which you can refer, and these names are typically hierarchical. So in order to use generate, you need some special variables which tell you how many times to repeat or generate. These are called genvar type variables. The keyword genvar is used for the purpose. So you can use this keyword to declare such variables which are used only for the generation of the blocks. These variables will be ignored during simulation or synthesis. These variables will only be required or used during the generation of the code, right. And these genvar variables, they are defined only within a generate loop and can be used there. And means I mentioned earlier that you can have a, and that let's here we are taking a very simple example of a bitwise exclusive OR. Like let's say what I'm saying, I'm taking a problem. Let's say I have a variable a, I have a variable b, which is multi-bit variable. Let's say this is 0101, this value is 0011, let's say. And suppose I am wanting to carry out bit by bit exclusive OR of these bits, and the result, let's call it f. So 1 and 1, if you take exclusive OR, it is 0, 0 and 1 will be 1, 1 and 0 will be 1, 0 and 0 will be 0. So this bitwise XOR, I want to do a parameterized design using genvar, using generate, where I can use it for any arbitrary n, for any arbitrary n bit numbers. So the idea is that if you want to do one XOR, 1 bit XOR, you need to make one instantiation of an XOR gate, like for example AB, that you can write XOR, you can give the name, say a name 0, then you can write F0, like for example AB, that you can write XOR, you can give the name, say a name 0, then you can write F0, A0, B0, like this. Then for the second bit, you can generate another XOR gate, XOR G1, F1, A1, B1, and so on. So what I'm saying now is that we want to define a parameter n, so that n copies of such XORs will be automatically generated. So I do not have to write so many XORs. This n can be 32, 64, whatever, right? So this is the example. Let us see. This is my Verilog code and this is the test bench. This is the Verilog code. So what I've written, let's see. This is the name of the module, 3 parameters. Here f, a and b, and here we have defined a parameter n, which for the sake of example we have taken it to be 16. So a and b, these are the inputs. We are declaring it to be inputs from bit number 0 up to n minus 1, a and b, and similarly f is the output, similarly it is a vector 0 to n minus 1. And we are declaring a genvar p, which p is a variable which we will be using inside this loop. Here you see use p. And this is how we can use a generate loop. Generate a for loop. Generate for p equal to 0, p less than n, p equal to p plus 1. It is exactly like a for loop, but it starts with a keyword generate and it ends with end generate, right. So, what it will mean is that whatever is there inside this begin end, this will be instantiated n times 0 up to n minus 1. So, what I have given inside this loop, you see I have defined a label, XOR LP is the label. I have given a label of this loop, and inside this I have instantiated one XOR gate. XOR I have given the name as XG, F this P, AP, BP. You see here we are given F0, A0, B0, F1, A1, B1. So, generally I am calling it as P, right. So, I call it BP, AP, FP. This is all. So if I just write this and I give it to the Verilog simulator or the synthesizer, it will be generating n copies of these XOR gates. So, here I have written it only once. So, suppose n is 16 such XOR lines will be generated automatically. So, we have we can basically test this code out using a test bench like this. I have also showed a test bench, you can try it out. Here we have instantiated this XOR bitwise function. We just use this named convention of passing arguments. This FAB was here, and here in this test bench we are calling them X, Y and out. Okay, X, Y are 16 bits, out is a 16 bits. Initial we are monitoring X, Y and out, and we are just applying two sample inputs. The first input is that first input X we are applying a 16-bit hexadecimal number A, and Y we are applying 00FF, and after a delay of 10 we are applying X equal to 0F and Y is 3333. Finish. So, if you actually run this, you get an output like this. You see A and and 00FF. This A is 1010, you see 1010 A, 1010, 1010, 100, and 00FF, bit by bit XOR. 1 and 0 is 1, 0 and 0 is 0. So, the first 8 bits will be like this 1010, and the last one will all be inverted. 1 and 0 XOR is 1, 1 and 1 XOR is 0, 0F, and this is the simulation result. Now, you see this XOR LP and this XOR. Now, the point is that XOR LP, this was the name we had given to the generate loop, right. So, these 16 copies of the XOR gates that will be generated, we have given the name as XG, okay, but there will be 16 such gates. What will be the names? Because in this example I was trying to write, I was writing but there will be 16 such gates. What will be the names? Because in this example, I was trying to write, I was writing G0, G1, G2 like this. But here I wrote it only once, xg. So what will be the name that will be generated for the 16 copies of these OR gates? They will be like this: XOR LP 0.xg, XOR LP 1.xg, dot 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 up to XOR LP 15.xg. So whatever loop variable you have defined, that will be treated as a vector, and you can use it with an index. Put a dot, and whatever variable name you have defined, you can use it after that. So like this, you can uniquely refer to the 16 XOR gates, right? Let's take a uniquely. So what I was trying to write for the (16 copies of these OR gates. They will be like this: XOR LP 0.xg, XOR LP 1.xg, dot 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 up to, right. So these 16 copies of the XOR gates that will be generated, we have given the name as xg, okay. But there will be 16 such gates. What will be the names? Because in this example, I was trying to write, I was writing G0, G1, G2 like this. But here I wrote it only once, xg. So what will be the name that will be generated for the 16 copies of these OR gates? They will be like this: XOR LP 0.xg, XOR LP 1.xg, dot 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 up to XOR LP 15.xg. So whatever loop variable you have defined, that will be treated as a vector, and you can use it with an index. Put a dot, and whatever variable name you have defined, you can use it after that. So like this, you can uniquely refer to the 16 XOR gates, right. Let's take another example, just like the ripple carry adder I talked about. Well, we start by giving you a structural description of a full adder. This is a gate level description of a full adder that consists of 2 XOR gates, 2 AND gates, and 1 OR gate. I showed this circuit earlier, you can just check it out. This is a compact gate level representation of a full adder. So the first 3 parameters are the inputs, then sum and carry out. So what we want to do now, so we want to use it using generate to create an n bit ripple carry adder. Let's see how. To create an n-bit ripple carry adder.